Tonight, we're going to Pluto, a world so cold that nitrogen falls out of the atmosphere and freezes onto the ground, where mountains are made of water ice as hard as rock, and where the sky is filled with a faint blue haze stretching hundreds of kilometers above the surface. For most of the last century, Pluto seemed simple, small, distant, frozen, and probably dead. Then, in 2015, New Horizons finally flew past it, after a journey of more than 9 years. What it found immediately broke that picture. Pluto had enormous glaciers of nitrogen ice, towering mountains, moving surface material, a layered atmosphere, and terrain so young that parts of it appeared to have been resurfaced relatively recently. And then, the James Webb Space Telescope looked again. This time, scientists were not just seeing Pluto's surface. They were measuring its heat, its chemistry, and the behavior of its atmosphere in wavelengths that New Horizons could not observe. What they found was stranger than anyone expected. Pluto's haze appears to help control the temperature of its atmosphere. Its frozen gases are constantly migrating across the surface. Material from Pluto can even escape into space and reach its largest moon, Charon. And now, new observations suggest something else may be happening. After decades of watching Pluto's atmosphere expand and stabilize, scientists may finally be seeing it begin to change as the dwarf planet moves farther away. Tonight, we're going to look at what scientists have actually discovered on Pluto, why this tiny frozen world turned out to be far more active than expected, and why nearly every time we look at it more closely, Pluto becomes stranger than it was before. That strangeness begins with Pluto's size. Its diameter is only about 2,377 kilometers. That makes Pluto smaller than Earth's moon, and gives it only a fraction of Earth's mass. On average, it orbits about 5.9 billion kilometers from the Sun, taking roughly 248 Earth years to complete a single trip around it. Out there, the available sunlight is extremely weak. Pluto's average surface temperature sits near -232 degrees Celsius, cold enough for substances that remain gases across most of Earth to freeze directly onto the landscape. Nitrogen, methane, and carbon monoxide can all exist as surface ices. Water behaves very differently. At Pluto's temperatures, water ice is so rigid that it forms the underlying crust and can support mountains several kilometers high. For decades, those conditions seem to point toward a fairly straightforward geological history. Pluto formed more than 4.5 billion years ago, along with the rest of the solar system. Like every planetary body, it began with heat left over from its formation, impacts, and the decay of radioactive elements in its rocky interior. But Pluto is small, and small worlds generally lose internal heat more efficiently than large ones. The reason comes down to geometry. Heat is stored throughout a body's volume, while most of that heat escapes through its surface. As an object becomes smaller, the amount of surface area it has compared with its volume increases. A small, icy world therefore has less interior material available to store heat for every square kilometer of surface through which that heat can escape. Over billions of years, that should matter. A world Pluto's size was expected to cool substantially. Any early geological activity should have weakened. Its surface should have spent immense stretches of time collecting impact craters while internal motion gradually faded. That was the basic picture scientists carried into the New Horizons era. Pluto could still have seasonal frost moving across its surface, because sunlight can warm and vaporize volatile ices, even on a cold world. But large-scale geological renewal was much harder to anticipate. Mountain building, active glaciers, convecting ice, possible cryovolcanoes, and evidence consistent with a buried ocean demanded additional sources of energy and much more complicated physics. The difficulty was that almost none of this could be seen from Earth. From our side of the solar system, Pluto is so distant and physically small that even powerful telescopes spent most of the 20th century seeing little more than a faint point of light. Its entire disk occupies only a tiny fraction of an arcsecond in our sky. A mountain several kilometers tall, or a glacier hundreds of kilometers wide, could exist there without revealing its true form in an ordinary telescope image. So for the first 85 years after Pluto was discovered, humanity was trying to understand an entire world from clues that were barely larger than a few blurred patches. And hidden inside those patches was a surface that would eventually overturn almost every simple expectation scientists had formed about Pluto. The first person to recognize Pluto as a new world was a 24-year-old farm boy from Kansas named Clyde Tombaugh. In early 1930, Tombaugh was working at Lowell Observatory in Flagstaff, Arizona, photographing the same areas of sky several nights apart. Each exposure was made on a glass photographic plate. He then placed pairs of plates into a machine called a blink comparator, which rapidly switched the view between them. Distant stars remained fixed. Anything moving through the solar system seemed to jump back and forth. On February 18th, Tombaugh noticed one faint point doing exactly that. The object had been photographed on January 23rd and again on January 29th. Its slow movement against the background stars showed that it was much closer than those stars, although still extremely far from Earth. Lowell Observatory announced the discovery publicly on March 13, 1930. For decades afterward, Pluto remained little more than that moving dot. The problem was angular size. A telescope does not see an object's true physical width. It sees the angle that object occupies in the sky. Pluto is more than 2,000 kilometers across, but from several billion kilometers away, its disk is only about 1/10 of an arcsecond wide when viewed from Earth. An arcsecond is a tiny unit of angle. A full circle contains more than 1 million arcseconds. At Pluto's apparent size, even a powerful telescope has very little room to separate one feature from another. Mountains, several kilometers high, disappear into the same blurred patch as the terrain around them. Large glaciers merge into broader regions of brightness. Fine boundaries between different kinds of ice become impossible to distinguish directly. For much of the 20th century, astronomers therefore learned about Pluto indirectly. They measured its motion, brightness, and changing position. Spectroscopy revealed clues about materials on its surface by separating reflected light into different wavelengths. Then, in 1978, another point of light changed the picture. Astronomer James Christie was examining images of Pluto taken at the United States Naval Observatory when he noticed that the dwarf planet sometimes appeared slightly elongated. The distortion shifted position from one image to another. Christie realized he was seeing a companion orbiting Pluto. That companion became Charon. Charon is roughly 1,200 kilometers across, making it about half Pluto's diameter. Compared with the primary world it circles, that is enormous. The two bodies are so similar in scale that their shared center of mass lies outside Pluto itself, a relationship very different from the Earth and Moon system. A decade later, Pluto produced another surprise, without anyone resolving its surface. On June 9, 1988, Pluto passed directly in front of a distant star as seen from Earth. Astronomers watched the star dim as Pluto crossed in front of it. Instead of disappearing instantly behind a sharp, solid edge, the starlight faded gradually. That gradual fading revealed an atmosphere. The technique is called a stellar occultation. As starlight passes through the thin layers of gas surrounding a world, the atmosphere bends and absorbs some of that light before the solid body blocks the star completely. The pattern of fading can reveal atmospheric pressure and temperature, even when the atmosphere itself cannot be photographed in detail. By the 1990s, the Hubble Space Telescope finally began producing crude maps of Pluto's disk. Broad, bright areas appeared beside darker regions. Astronomers could see that the surface was not uniform and that its appearance changed as Pluto rotated. The maps still lacked anything resembling the detail of photographs from Mars or Jupiter. A 1,000-kilometer region might register as little more than a change in brightness. Individual mountains remained invisible. Sputnik Planitia had not yet appeared as a recognizable glacier. The enormous water ice blocks surrounding it were hidden inside pixels that blended large areas together. Pluto grew more complicated again in the early 21st century. Hubble observations revealed 2 additional moons, Nix and Hydra, in 2005. Kerberos was found in 2011, followed by Styx in 2012. Together with Charon, Pluto now had 5 known moons orbiting a body smaller than Earth's moon. By then, astronomers knew Pluto possessed an atmosphere, a complex surface, and an unusually large family of satellites. They could measure some of its chemistry and watch seasonal changes from billions of kilometers away. The important details were still below the limit of what remote telescopes could resolve. To see what Pluto's surface was actually doing, an instrument would have to leave Earth behind, cross the outer solar system, and pass close enough for mountains and glaciers to separate into individual features. The spacecraft chosen for that job was New Horizons, a compact probe built for speed. It launched from Cape Canaveral on January 19, 2006, aboard an Atlas V rocket. Once the upper stage finished its work, New Horizons was leaving Earth faster than any spacecraft had before. Its departure speed was more than 58,000 kilometers per hour. At that pace, it crossed the distance of the Moon's orbit in roughly 9 hours. That speed was necessary because Pluto was still billions of kilometers away. Even a spacecraft moving tens of thousands of kilometers per hour would need years to reach it, and New Horizons was designed around a single narrow opportunity to pass through the Pluto system. The probe itself was about the size of a grand piano. It carried 7 scientific instruments, including cameras, spectrometers, a dust detector, and a radio experiment used to study Pluto's atmosphere. Power came from a radioisotope generator rather than solar panels, because sunlight in the outer solar system is far too weak for a small spacecraft to rely on ordinary solar power efficiently. New Horizons did not travel directly to Pluto at a constant speed. Its path used Jupiter as a giant gravitational accelerator. On February 28, 2007, a little more than 13 months after launch, the spacecraft passed Jupiter at a distance of roughly 2.3 million kilometers. As New Horizons fell into Jupiter's enormous gravitational field, the planet pulled the spacecraft inward and increased its speed. The spacecraft then swung around Jupiter and escaped along a new path aimed more closely toward Pluto. This maneuver is called a gravity assist. The useful part comes from the fact that Jupiter itself is moving around the Sun at roughly 13 kilometers per second. During the encounter, New Horizons exchanged a tiny amount of orbital energy and momentum with the moving planet. Jupiter's own motion changed by an amount far too small to measure meaningfully, while the much lighter spacecraft gained a substantial increase in speed. The assist added roughly 14,000 kilometers per hour to New Horizons' velocity toward Pluto. Without that encounter, the trip would have taken years longer. Jupiter also gave the mission team a chance to test the spacecraft's instruments in a real planetary encounter. New Horizons photographed Jupiter's atmosphere, watched volcanic activity on the moon Io, studied the planet's rings, and practiced the tightly scheduled observing sequences that would later be needed at Pluto. After Jupiter, the solar system became much quieter. For long stretches of the journey, New Horizons entered hibernation. Most systems were powered down while the spacecraft continued outward. Mission controllers woke it periodically to check its health, update software, and make small corrections to its trajectory. The cruise lasted year after year. Saturn's orbit fell behind. Then Uranus's distance was crossed. Neptune's orbit was passed in August of 2014, almost exactly 25 years after Voyager 2 had flown past Neptune. By early 2015, Pluto was finally growing from a point into a world. Each new image showed more structure than the last. Bright and dark regions appeared. The large, heart-shaped area, later named Tumba Regio, became visible. Charon separated clearly from Pluto. Smaller moons moved around the pair. On July 14, 2015, New Horizons reached its closest approach. The spacecraft passed about 12,500 kilometers above Pluto's surface. It was moving at roughly 14 kilometers per second relative to Pluto, fast enough to cross the width of the continental United States in only a few minutes. There was no way to break into orbit. Carrying enough fuel to slow a spacecraft from that speed would have made the mission far heavier and more expensive. New Horizons was built as a flyby probe, so every important observation had to be planned in advance. During closest approach, the spacecraft actually turned its main antenna away from Earth so its instruments could point toward Pluto and Charon. Mission controllers could not steer it moment by moment. A command sent from Earth took about 4.5 hours to arrive, and a response required another 4.5 hours to return. For the most important part of the encounter, New Horizons was effectively on its own. Its cameras swept across Pluto's surface. Spectrometers measured surface composition. Instruments sampled ultraviolet light passing through the atmosphere. Radio signals later probed atmospheric pressure and temperature. Then the spacecraft was already moving away. Humanity had spent more than 9 years crossing the solar system for a close encounter measured in hours. When the first detailed images began arriving back on Earth, scientists quickly noticed something extraordinary in the bright heart-shaped region. Large areas of its surface showed remarkably few impact craters, as though part of Pluto had been resurfaced far more recently than anyone expected. The bright heart-shaped region that had begun to appear in distant approach images soon became the most recognizable feature on Pluto. Scientists named it Tumba Regio, after Clyde Tombaugh. Its western half contained a broad, smooth basin that looked almost unnaturally clean compared with the battered surfaces expected on an ancient world. That basin was named Sputnik Planitia. It stretches roughly 1,000 kilometers across. At first glance, Sputnik Planitia resembles a pale, frozen plain. Closer images from New Horizons showed a surface divided into large cells, bordered by darker troughs, and scattered with unusual pits and ridges. More important than any individual shape was something largely missing from the landscape: impact craters. Across much of Sputnik Planitia, scientists could find very few of them. Some areas appeared essentially crater-free at the resolution New Horizons could achieve. That absence immediately mattered, because impact craters provide planetary scientists with one of their most useful ways to estimate the age of a surface. The solar system has contained asteroids, comets, and smaller fragments for billions of years. Over long periods, some of those objects collide with planets and moons. a surface that remains exposed for several billion years, gradually accumulates scars. The Moon is a familiar example. Its ancient highlands are densely covered with overlapping craters because much of that terrain has remained exposed for an immense span of time. On Earth, many old impact scars have been erased by erosion, plate tectonics, sediment, and volcanic resurfacing. Pluto has no rain, carving rivers through its crust, and no system of moving rocky plates like Earth. If its surface had remained largely unchanged since the early solar system, scientists expected many regions to preserve a substantial record of impacts. Sputnik Planitia did not. Researchers compared crater densities across different parts of Pluto and found a landscape with strikingly different ages. Some darker, heavily cratered regions appeared to have survived for billions of years. Other terrain was much younger. The smooth plains inside Sputnik Planitia represented the extreme case. Early analysis after the flyby suggested parts of this terrain could be less than about 100 million years old. Some estimates allowed portions of the surface to be far younger, perhaps only around 10 million years old. Those numbers are young on a planetary timescale. 100 million years sounds enormous in human terms. Compared with Pluto's age of more than 4.5 billion years, it represents only a small fraction of the dwarf planet's history. The conclusion did not require Pluto itself to have formed recently. Something had renewed the upper surface long after Pluto formed. An impact could create fresh terrain locally, but the broad, smooth plains showed no obvious pattern of being a single recent crater floor. Instead, new horizons revealed a vast deposit of volatile ice, filling a deep basin. The basin itself is probably ancient. Sputnik Planitia is widely interpreted as an enormous impact structure formed much earlier in Pluto's history. What sits inside it has remained active enough to obscure much of the impact record that would otherwise reveal its age. New horizons also showed that Sputnik Planitia is exceptionally deep. Estimates place portions of the basin several kilometers below surrounding terrain. That depression has become a natural collecting area for some of Pluto's most volatile materials. Nitrogen dominates much of the visible ice there. Carbon monoxide and methane are mixed into parts of the deposit as well. These substances behave very differently from the water ice forming much of Pluto's harder crust. At the temperatures found on Pluto, water ice is extremely rigid. Nitrogen ice is much softer. Given enough thickness and enough time, it can deform. That distinction changed the meaning of the smooth surface. A crater forming in rigid water ice might remain visible for an enormous period. A crater forming in a thick deposit of mobile nitrogen ice can gradually lose its shape as the surrounding material moves. The plain, therefore, carries evidence of an active resurfacing process. Older scars can be softened, buried, or removed as fresh material replaces what was previously exposed. The scale of the deposit makes that process especially important. Sputnik Planitia is often described as the largest known glacier in the solar system, extending across an area comparable to a large region of North America. Its smoothness was the first clear indication that Pluto still possessed enough ongoing activity to renew enormous parts of its landscape. The material responsible would have seemed almost weightless on Earth. Here, nitrogen is a major component of the air around us. On Pluto, the same substance can accumulate in layers kilometers thick and slowly move across the surface like a glacier. Inside Sputnik Planitia, the material responsible for much of that resurfacing is frozen nitrogen. At Pluto's surface temperature, nitrogen can accumulate as solid ice rather than remain a gas. Methane and carbon monoxide are mixed through parts of the basin as well, creating a landscape built from substances that behave very differently from the water ice underneath them. That difference is important because Pluto effectively has two kinds of ice doing two different geological jobs. Water ice forms much of the strong structural crust. At temperatures near -230 degrees Celsius, it is extremely rigid. Large blocks of it can support mountains several kilometers high without slowly collapsing under their own weight. Nitrogen ice is softer. Given enough pressure and enough time, a thick layer of nitrogen can deform while remaining completely solid. The individual molecules stay locked into a crystalline material, but the entire mass can slowly change shape. The same basic principle operates in glaciers on Earth. A terrestrial glacier is solid water ice, yet gravity can make it creep downhill over years and centuries. Ice deeper inside the glacier is squeezed by the weight above it, allowing the mass to deform and flow around obstacles. A person standing beside one would see something apparently motionless. Measurements taken years apart reveal that the entire landscape has shifted. Sputnik Planitia behaves in a similar way with nitrogen. New Horizons photographed features along the edges of the basin that appear to show nitrogen-rich ice moving out of surrounding uplands and into the lower plain. Lobes of material extend through valleys. Flow patterns appear where the ice has passed around obstacles. Some channels seem to connect elevated reservoirs with the larger deposit below. The basin gives all of this material somewhere to collect. Sputnik Planitia stretches roughly 1,000 kilometers from side to side. NASA has compared the area of the glacier with Texas and Oklahoma combined. Models based on its shape and surrounding topography indicate that the nitrogen layer may be several kilometers thick in places, with estimates around 4 kilometers or more for portions of the deposit. That much ice creates enormous pressure at depth. Pluto's gravity is only about 6% of Earth's, so the weight pressing downward is much weaker than it would be here. Even so, kilometers of overlying nitrogen are enough to influence how the lower layers behave. The glacier also occupies one of the lowest large regions on Pluto. Material moving downhill from surrounding terrain naturally tends to enter the basin and remain there. Once inside, it can gradually cover older surfaces. Imagine an impact crater forming in a relatively rigid part of Pluto's crust. Its rim and bowl may remain visible for an immense period. Inside a mobile nitrogen deposit, the same shape is exposed to continuous deformation. Ice can move across the crater floor, soften the rim, fill the depression, and eventually make the original scar difficult to recognize. Fresh frost can add another layer. Nitrogen from the atmosphere can condense directly onto the surface when temperatures fall. Later warming can return some of that ice to the atmosphere through sublimation. Sputnik Planitia therefore changes through more than one process at once. Glacial flow moves material across the landscape, while seasonal exchange moves nitrogen between the ground and the atmosphere. Those processes help explain why parts of the basin look so young. They also show why describing Pluto simply as frozen can be misleading in an everyday sense. Its surface is certainly cold enough to keep nitrogen solid for long periods, but solid material can still move. A landscape does not need rivers of liquid to remain active. The speeds involved are extremely slow compared with flowing water. Pluto's glaciers can move over years, centuries, and much longer intervals. Their effect becomes large because the process continues across enormous areas. Over geological time, even movement measured in centimeters or meters can reshape a basin hundreds of kilometers wide. New Horizons found evidence that this motion extends beyond ice creeping sideways across the surface. The large polygonal cells covering Sputnik Planitia suggest that parts of the glacier are also circulating from below, with nitrogen ice rising and sinking through a layer several kilometers deep. Across the center of Sputnik Planitia, New Horizons photographed a pattern that looked almost geometric. The nitrogen plane was divided into broad polygonal cells, many at least 10 kilometers across. Some extended much farther. From above, they resembled a field of enormous tiles, separated by shallow troughs and darker boundaries. These shapes were one of the clearest signs that the glacier was doing more than creeping slowly across Pluto's surface. Researchers interpreted them as convection cells. Convection happens when material moves because of small differences in temperature and density. On Earth, it is easy to picture in a pot of water warming on a stove. Warmer water near the bottom becomes slightly less dense and rises. Near the top, it cools and sinks again. Inside Sputnik Planitia, the same general process appears to happen within solid nitrogen ice. The glacier is thought to be several kilometers thick in places. Heat reaching the bottom of that layer, whether from Pluto's interior or from stored energy within the ice, makes the deepest nitrogen slightly warmer than the material above it. The temperature difference does not need to be dramatic. Nitrogen ice at Pluto's surface conditions is soft enough that even small changes in temperature can alter how easily it deforms. Slightly warmer material at depth becomes more buoyant and begins moving upward. Near the surface, where it loses heat, the nitrogen becomes denser and gradually sinks along the edges of the cell. A single cycle can take an enormous amount of time. The motion is measured on geological scales rather than anything a person could watch directly. Models suggest the overturning may occur over hundreds of thousands to millions of years, depending on the thickness, temperature, and physical properties of the ice. That is still fast enough to matter on a world more than 4.5 billion years old. The center of each convection cell tends to rise slightly while the boundaries between cells become places where colder material descends. Over time, those movements can continuously replace the exposed upper surface with nitrogen that was previously buried deeper in the glacier. That gives Sputnik Planitia another way to erase its own history. An impact crater does not need to be actively filled by a sudden flood of material. Slow overturning can deform the surface beneath it, disturb the crater walls, and gradually replace the upper layers. The result is a landscape that can stay surprisingly smooth, despite existing in a part of the solar system where impacts have been occurring for billions of years. New Horizons also saw subtle ridges and pits associated with the cell boundaries, along with variations in brightness that appear to reflect differences in surface texture and composition. Taken together, the features made Sputnik Planitia look less like a frozen sheet resting motionless inside a basin, and more like a very slow-moving layer that is continually renewing itself from within. The scale makes the process difficult to imagine. A convection cell, 10 kilometers wide, would span much of a large city. Several of them, placed side by side, can fill a region hundreds of kilometers across. Beneath the visible surface, nitrogen may be circulating through a layer kilometers deep. On Earth, convection often brings to mind molten rock in the mantle or hot water in a heated container. On Pluto, a similar physical principle can operate inside solid nitrogen at temperatures close to -230 degrees Celsius. That discovery helped explain why the plane contained so few craters, but it also changed the way scientists thought about Pluto's geology. A landscape could remain active even when almost every familiar substance was frozen solid. Beyond the edges of Sputnik Planitia, New Horizons revealed another part of that altered picture. Rising above the softer nitrogen were steep mountains, several kilometers tall, built from water ice strong enough at Pluto's temperature to behave almost like stone. Along the margins of Sputnik Planitia, the landscape rises sharply. New Horizons photographed rugged ranges where individual peaks reach roughly 2 to 3 kilometers above the surrounding terrain. Some of these mountains stand along the western edge of the nitrogen plain, appearing as steep blocks pushed together beside the smoother glacier. Their composition surprised scientists almost as much as their height. Spectral measurements showed that much of Pluto's mountainous terrain is built from water ice. On Earth, that sounds fragile. Glaciers crack, icebergs break apart, and ordinary ice melts at temperatures humans encounter every year. Pluto changes those familiar properties. Near the surface, temperatures commonly remain around -230 degrees Celsius. Water molecules have so little thermal energy under those conditions that the ice becomes extremely stiff. It can support enormous cliffs and mountain-sized blocks, while deforming far more slowly than the nitrogen ice surrounding it. Water, therefore, plays much the same structural role on Pluto that silicate rock plays on Earth. That comparison helps explain why the mountains can exist directly beside Sputnik Planitia. The nitrogen filling the basin is comparatively soft and volatile. It can creep through valleys and slowly flow around obstacles. Water ice forms the harder framework underneath, creating elevated terrain that the nitrogen glacier must move past or over. New Horizons revealed some particularly dramatic examples near the eastern and western margins of Tumbor Regio. The range called Norgay Montes contains rugged peaks, rising several kilometers above nearby plains. Farther north, another mountainous region was named Hillary Montes. Individual blocks there are tens of kilometers across in some images, large enough that they resemble fragments of crust rather than ordinary hills. Scientists also found isolated water ice blocks apparently embedded within Sputnik Planitia itself. Some have been compared with floating icebergs. The comparison is useful because nitrogen ice is denser than water ice under Pluto's surface conditions. Large chunks of water ice crust can therefore be supported within the softer nitrogen-rich material, although their movement is extraordinarily slow. A block, several kilometers across, could gradually be carried as the surrounding nitrogen shifts. This creates a landscape with a strange division of labor between different frozen substances. Water ice supplies much of the rigid foundation. Nitrogen can flow through low terrain and gather inside deep basins. Methane and carbon monoxide can freeze onto parts of the surface as additional volatile layers, changing with temperature and season. Those materials can also coat the mountains. New Horizons found evidence that some high-altitude terrain contains methane frost. At Pluto's low atmospheric pressure, volatile molecules can move between the surface and atmosphere, then condense in colder locations. Elevated terrain can therefore develop coatings that differ from the harder water ice underneath. The result resembles a rocky mountain range dusted with snow, except the underlying rock is frozen water and part of the frost can be frozen methane. These differences come from phase behavior, meaning the way a substance changes between solid, liquid, and gas as temperature and pressure vary. On Earth, water sits close enough to its melting point that ice is relatively easy to soften or melt. Nitrogen remains gaseous through most ordinary surface conditions. Pluto places both substances in a very different part of their physical range. At roughly 40 Kelvin, nitrogen can form broad deposits that deform over time. Water ice remains far below its melting point and becomes a strong crustal material capable of holding up mountains. That layered structure gives Pluto a more complex geology than its smooth appearance from Earth ever suggested. Beneath the volatile surface deposits lies a framework of rigid water ice. Across that framework, softer frozen gases migrate and accumulate. The boundary between them can create cliffs, broken blocks, and glacial pathways extending for hundreds of kilometers. Some structures discovered farther from Sputnik Planitia were harder to explain with ordinary glacial movement. They formed broad rises several kilometers high, with enormous depressions near their centers and terrain that looked as though material had been piled upward from below. Their shape raised the possibility that Pluto possesses something resembling volcanoes, built from substances very different from molten rock. Southwest of Sputnik Planitia, the terrain becomes rougher and rises into a cluster of enormous mounds. Two of the largest are called Wright Mons and Picard Mons. New Horizons photographed both during its July 2015 flyby, and their shapes immediately drew attention because they resembled structures built by material coming up from below. Wright Mons rises roughly 4 to 5 kilometers above the surrounding terrain and spans about 150 kilometers. Near its center is a broad depression, roughly 40 to 50 kilometers across. Picard Mons is even larger, reaching about 7 kilometers high in places and extending roughly 225 kilometers from side to side. These are enormous structures for a world only about 2,377 kilometers across. Their surfaces are also unusual. The flanks of Wright Mons are covered with hummocky terrain, meaning the ground consists of broad, rounded rises and depressions rather than smooth slopes. Many of these hummocks are several kilometers across. Smaller ridges and blocks sit on top of them, producing a landscape that looks as though large volumes of material were placed there in multiple episodes. The central depression of Wright Mons adds to the mystery. It reaches several kilometers deep, almost down to the level of the surrounding landscape. Its size and shape differ from the familiar summit craters seen on many volcanoes on Earth or Mars. Researchers studying the topography have suggested that Wright Mons may actually consist of several large rises that merge together over time. The leading explanation involves cryovolcanism. Cryovolcanism is volcanic activity involving substances that remain frozen near a world's surface. On a rocky planet such as Earth, volcanic material is usually molten silicate rock. Pluto's interior contains large amounts of water ice, so a cryovolcanic eruption could involve warmer, water-rich material mixed with other compounds that make it easier to flow. Ammonia is especially important in these models. Pure water freezes at 0 degrees Celsius under ordinary Earth conditions. Mixing ammonia into water lowers the freezing temperature substantially. Inside an icy world, that allows a water-ammonia mixture to remain softer, slushy, or partly liquid at temperatures where pure water would already be solid. If such material rose through fractures in Pluto's crust, it could spread across the surface and freeze into thick deposits. Researchers analyzing the Wright Mons region have estimated that the main rise alone contains roughly 24,000 cubic kilometers of material. That is comparable in volume to Mauna Loa in Hawaii, one of the largest volcanoes on Earth. The surrounding landscape strengthens the cryovolcanic interpretation. Large rises extend between Wright Mons and Picard Mons, with similar textures and elevations. Their arrangement suggests that the region may have been resurfaced by repeated episodes rather than produced by a single isolated event. That distinction matters because a single ancient eruption could be easier to reconcile with a world that became inactive long ago. Multiple construction episodes imply that Pluto retained usable internal heat for a substantial part of its history. The source of that heat is still being studied. Pluto formed more than 4.5 billion years ago, and its rocky interior contains radioactive elements such as uranium, thorium, and potassium. Their gradual decay releases heat over immense periods. Even today, the same process warms the interiors of planets and moons throughout the solar system. Pluto's small size allows heat to escape relatively efficiently, so maintaining enough warmth to mobilize material deep underground requires the interior to lose energy slowly enough for some of that heat to remain. An insulating shell of water ice could help. So could compounds such as ammonia, which allow icy mixtures to move without reaching the melting point of pure water. No spacecraft has watched Right Mons erupt. New Horizons passed Pluto only once, and the cryovolcanic interpretation comes from the shapes, compositions, and geological relationships preserved in the terrain. That evidence is strong enough for scientists to take the possibility seriously, while still leaving room for other explanations. Even that possibility changes the picture of Pluto's interior. Surface nitrogen glaciers can be powered largely by solar heating and seasonal cycles. Building structures several kilometers high from material rising through the crust requires energy stored much deeper down. If enough internal warmth survived to produce cryovolcanic terrain, Pluto may also have preserved something far larger beneath its frozen crust. Models of its interior allow for a layer of liquid water that could still exist tens or even hundreds of kilometers below the surface. Deep beneath Pluto's surface, that retained heat may have preserved an environment very different from the frozen landscape above it. One of the strongest clues comes from Sputnik Planitia itself. The giant nitrogen glacier occupies a basin roughly 1,000 kilometers across, probably created by an enormous impact early in Pluto's history. The collision would have excavated a vast amount of crust, leaving a depression that later filled with kilometers of nitrogen-rich ice. Its location is unusually important. Sputnik Planitia sits close to the line connecting Pluto with Charon, the large moon that keeps the same face toward Pluto as the two worlds orbit their shared center of mass. Researchers studying New Horizons data found that this placement is unlikely to be random. The basin may have helped Pluto slowly reorient. Planetary scientists call this process true polar wander. Despite the name, the entire solid outer shell can shift its orientation relative to a world's spin axis. If a large region becomes unusually heavy, rotation and tidal forces can gradually favor a position where that extra mass lies closer to a stable gravitational alignment. Earth has probably experienced smaller forms of this process during its history. On Pluto, the effect may have been dramatic enough to move Sputnik Planitia by hundreds or even thousands of kilometers across the globe. That creates a puzzle. An enormous impact normally removes material and leaves a basin with less mass than the surrounding crust. Sputnik Planitia is filled with nitrogen ice, and that ice adds weight back into the depression. Models suggest the nitrogen alone may not fully explain the positive mass concentrated there. Something denser beneath the basin could contribute. A buried ocean provides one possible explanation. If Pluto contains a deep layer of liquid water beneath its frozen crust, the impact that formed Sputnik Planitia could have thinned the ice shell above that ocean. Denser liquid water could then sit closer to the surface beneath the basin than it does elsewhere on Pluto. Combined with the thick nitrogen deposit above, that arrangement could create enough excess mass to help pull Sputnik Planitia toward its present location. The proposed ocean would lie far below anything New Horizons could photograph directly. Interior models generally place a possible liquid layer beneath many tens of kilometers of water ice. Its exact depth and thickness depend on Pluto's composition, the amount of heat remaining inside it, and how effectively the outer ice shell insulates the interior. Keeping water liquid for more than 4 billion years requires a slow loss of heat. Radioactive elements inside Pluto's rocky core can provide a continuing source. Compounds, such as ammonia, can also lower the freezing temperature of water, allowing liquid or partially liquid mixtures to survive at lower temperatures. New Horizons found another clue written across Pluto's crust. Large fractures extend for hundreds of kilometers. Some form deep troughs, bordered by steep walls. One of the largest systems, Virgil Fossa, runs across the surface for several hundred kilometers and reaches widths of several kilometers. These fractures show that Pluto's crust has experienced large-scale stretching. A slowly freezing internal ocean could help produce that pattern. Water expands when it freezes. If a global ocean beneath Pluto gradually turned into additional ice, the increase in volume would place the outer shell under tension. Over long periods, that stress could pull the crust apart and create enormous fractures. The idea also helps explain why scientists have not found widespread evidence that Pluto experienced the opposite process of strong global contraction. A world cooling completely from a warm interior might be expected to shrink and compress its crust. New Horizons instead revealed extensive terrain shaped by extension. None of these observations proves that a liquid ocean exists beneath Pluto today. The evidence comes from the way several independent features fit together. Sputnik Planitia's location, its unusual mass distribution, and the large fractures crossing the crust. Together, they allow a remarkable possibility. A dwarf planet with a surface temperature near -230 degrees Celsius may still contain liquid water deep inside. Yet some of Pluto's most active cycles occur much closer to the surface. There, nitrogen can move between two entirely different states as sunlight changes, causing parts of the frozen ground to vanish directly into the atmosphere. Near Pluto's surface, nitrogen moves through a cycle that connects the ground directly to the atmosphere. The atmosphere itself is extremely thin. It is made mostly of molecular nitrogen, with smaller amounts of methane and carbon monoxide mixed through it. Near the surface, the pressure is only a tiny fraction of Earth's, measured in microbars rather than the roughly 1 bar we experience at sea level. A microbar is 1/1,000,000th of a bar. That means Pluto can possess a real atmosphere while still having so little gas above its surface that a person standing there would experience something much closer to a vacuum than to ordinary air. The material in that atmosphere also comes directly from the landscape. When sunlight warms exposed nitrogen ice, some of the solid molecules gain enough energy to escape from the surface and become gas. This process is called sublimation. Sublimation allows a substance to move directly from solid to gas without first becoming liquid. Dry ice on Earth does something similar. Frozen carbon dioxide does not normally melt into a puddle at ordinary atmospheric pressure. It changes directly into gas. On Pluto, nitrogen can behave in the same general way. A patch of nitrogen ice, receiving slightly more sunlight, can slowly lose material into the atmosphere. That gas can travel across Pluto before reaching a colder region where it freezes back onto the ground. The return process is deposition, sometimes described simply as condensation onto the surface. Molecules in the atmosphere lose enough energy to become solid again, building layers of frost. Over time, this creates a global transport system. Nitrogen can leave one part of Pluto, cross hundreds or thousands of kilometers through the atmosphere, and become part of the surface somewhere else. Methane and carbon monoxide participate in related cycles, although each substance freezes and vaporizes under different conditions. Sputnik Planitia plays a major role because it contains such a large reservoir of volatile ice. Its broad, nitrogen-rich surface can exchange material with the atmosphere across an area hundreds of thousands of square kilometers in size. Changes in temperature there can influence the amount of gas surrounding the entire dwarf planet. The connection is especially sensitive because nitrogen vapor pressure changes rapidly with temperature. Vapor pressure is a measure of how strongly a solid or liquid tends to produce gas above itself at a given temperature. For nitrogen ice on Pluto, a change of only a few degrees can produce a large change in the amount of nitrogen gas the surface can support. A slightly warmer surface allows more molecules to escape. A slightly colder surface encourages more nitrogen to return to the ground. That makes Pluto's atmosphere unusually responsive to small thermal changes. The effect also means atmospheric pressure can rise or fall without adding any new material to Pluto as a whole. The same nitrogen simply moves between two reservoirs. At one moment, more of it may exist as frost and glacier ice. At another, a larger fraction may be suspended above the surface as gas. The total inventory remains connected. This is one reason Pluto's climate cannot be understood by studying the atmosphere alone. Surface temperature changes alter sublimation. Sublimation changes atmospheric pressure. Atmospheric transport then moves nitrogen toward colder regions, where it freezes again. The landscape and atmosphere continually reshape each other. Even the familiar appearance of Pluto's surface depends partly on this exchange. Bright volatile frosts can build up seasonally. Darker material becomes exposed where ice disappears. Some areas gain nitrogen while others lose it, changing the thickness and distribution of surface deposits over long periods. The atmosphere therefore represents part of Pluto's frozen surface temporarily lifted into the sky. How much material makes that transition depends heavily on sunlight. Pluto's distance from the Sun changes by billions of kilometers during each orbit, altering the amount of solar energy reaching its surface. Its extreme axial tilt also creates long seasons in which different regions receive sunlight for very different lengths of time. Those slow orbital changes control how much of Pluto's nitrogen remains frozen and how much becomes atmosphere over the course of centuries. Pluto's changing atmosphere is tied to an orbit that takes nearly 2.5 centuries to complete. One trip around the Sun lasts about 248 Earth years. A person born at 1 Pluto perihelion would be long gone before the dwarf planet returned to the same point in its orbit. That orbit is also much more stretched than Earth's. At its closest approach, Pluto comes to roughly 30 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. Near the farthest part of Pluto's orbit, the distance grows to about 49.3 astronomical units. That means Pluto's distance from the Sun changes by almost 3 billion kilometers between the closest and farthest portions of its path. The amount of sunlight changes with it. Solar energy follows what physicists call the inverse square law. If the distance from a light source doubles, the same amount of energy becomes spread across 4 times the area. A world moving farther away, therefore, receives less sunlight very quickly. Pluto never doubles its distance from the Sun over one orbit, but the change from about 30 to 49 astronomical units is still large enough to matter. Near perihelion, Pluto receives roughly 2.5 times as much solar energy as it does near aphelion. Even at its closest point, the sunlight is faint compared with Earth. At 30 astronomical units, the solar energy reaching each square meter is only about 1/900th of what Earth receives at the same angle. That weak sunlight still controls the movement of Pluto's volatile ices because nitrogen sits close to the temperatures where small changes can strongly affect sublimation. Pluto's axial tilt adds another layer. Its rotation axis is tipped by roughly 120 degrees when measured in the usual direction used for planetary rotation. That extreme geometry means Pluto effectively rotates on its side and in a retrograde direction compared with many planets. The result is long, unusual seasons. For decades at a time, One region can receive prolonged sunlight, while another spends long periods in shadow. As Pluto moves around its orbit, the pattern of heating shifts slowly across the surface. That matters for nitrogen because the warmest regions tend to lose volatile ice through sublimation. Colder areas can gain material as atmospheric nitrogen freezes back onto the ground. A seasonal change that might happen over a few months on Earth can unfold across many years on Pluto. The timing of the modern observations is especially useful. Pluto reached perihelion in 1989. That was the point in its orbit when it was closest to the Sun. Since then, it has been moving steadily outward. By the time New Horizons arrived in 2015, Pluto had already spent 26 years receding from perihelion. It continues moving farther away today. From a simple heating perspective, that should gradually reduce the energy reaching the surface. Over enough time, colder conditions should favor more nitrogen freezing out of the atmosphere and returning to the ground. Scientists therefore expected Pluto's atmosphere eventually to thin as the dwarf planet moved deeper into the colder part of its orbit. The transition is slow because Pluto's surface does not respond instantly. Large deposits, such as Sputnik Planitia, can absorb heat and release it gradually. The amount of nitrogen already stored in different regions also affects how quickly the atmosphere changes. This creates a seasonal lag. The same effect happens on Earth in a much milder form. The warmest part of a summer day usually occurs after local noon, even though noon is when the sun is highest in the sky. Land and water take time to warm. Pluto's version operates across years and decades. That long delay became visible in the atmospheric measurements. Pluto had been moving away from the Sun since 1989, yet observations through the following decades showed that its atmospheric pressure was still increasing. By the time New Horizons arrived, the atmosphere had become substantially denser than it had been when astronomers first detected it in 1988. The surface was cooling only gradually, while stored heat and shifting nitrogen ice continued feeding gas into the atmosphere. The seasonal system was responding to conditions from years earlier. For a world moving steadily farther into darkness, Pluto was holding on to more atmosphere than scientists had expected. By the time New Horizons reached Pluto in 2015, astronomers had been tracking its atmosphere for nearly 3 decades. One of the best tools for doing that remained the same technique that first revealed the atmosphere in 1988: stellar occultations. When Pluto passes in front of a distant star, the starlight fades gradually as it travels through Pluto's atmosphere before the solid body blocks the star completely. The exact shape of that fading can be used to estimate atmospheric pressure and temperature. Over repeated occultations, scientists began to see a long-term trend. Pluto's atmospheric pressure was increasing. That was unexpected because Pluto had passed its closest point to the Sun in 1989. After that, it began moving steadily farther away, receiving less solar energy each year. A simple picture would suggest that colder conditions should allow more nitrogen to freeze out of the atmosphere and return to the surface. Instead, observations through the 1990s, the 2000s, and into the New Horizons era showed the atmosphere becoming denser. The reason appears to involve thermal inertia. Thermal inertia describes how slowly a material changes temperature when the amount of heating changes. A dark rock sitting in sunlight can remain warm after the sun moves away because the stored heat takes time to escape. Oceans respond even more slowly. They absorb enormous amounts of energy and release it gradually. Pluto's surface works on a much longer timescale. Large nitrogen reservoirs, especially around Sputnik Planitia, can store heat accumulated during the decades near perihelion. As Pluto moves outward, those reservoirs do not cool immediately. The result is a seasonal lag. nitrogen ice can continue sublimating into the atmosphere even after the amount of sunlight reaching Pluto has begun to fall. This helps explain why atmospheric pressure kept rising after 1989. The pressure increase was substantial enough to be measured repeatedly from Earth. Observations from stellar occultations showed that the atmosphere became several times denser between the first detection in 1988 and the period around the New Horizons encounter. That long rise also tells us something important about the surface. The atmosphere cannot increase without material entering it. Since Pluto's atmosphere is supplied mainly by nitrogen sublimating from surface ice, a rise in pressure means large volatile reservoirs were continuing to release gas. Sputnik Planitia is central to many climate models because it contains such a large amount of nitrogen. Its broad surface can exchange material with the atmosphere over an area hundreds of thousands of square kilometers in size. Even a small temperature change across such a large reservoir can move a significant amount of nitrogen between the ground and the atmosphere. Pluto's atmosphere therefore remembers earlier seasons. The sunlight received in one decade can influence atmospheric conditions years later because the surface stores energy and releases it slowly. This delayed response becomes especially important on a world where the orbital period is 248 years. By the time New Horizons arrived in July of 2015, Pluto had been moving away from perihelion for 26 years. Yet the atmosphere remained robust. Occultation measurements after the flyby continued to show relatively high pressure. A combined analysis of observations through the early 2020s indicates that atmospheric pressure remained near a plateau from around the New Horizons period through approximately 2021. That suggests Pluto's atmosphere may have spent several years in a kind of delayed equilibrium. The dwarf planet was receiving less sunlight than it had near perihelion, but stored heat and ongoing nitrogen transport were still supporting a relatively dense atmosphere. This is the kind of seasonal behavior that is almost impossible to watch from beginning to end on a human timescale. The first atmospheric detection came in 1988. More than 30 years later, scientists were still observing the same broad seasonal response. That means an entire scientific career can pass while Pluto moves through only a small fraction of one climatic cycle. The atmosphere's slow evolution had already shown that distance from the Sun alone could not explain Pluto's climate at any single moment. New Horizons added another complication. When the spacecraft measured temperatures high in Pluto's atmosphere, the gas was colder than many earlier models had predicted. That meant scientists now had to explain both the atmosphere's unexpected persistence and the way it was losing heat. New Horizons measured Pluto's atmosphere in several different ways as it passed the dwarf planet in July of 2015. One instrument watched ultraviolet light from the Sun pass through the atmosphere as Pluto moved in front of it. Different gases absorb different wavelengths, so the changing ultraviolet signal revealed where nitrogen, methane, and other components were distributed with altitude. A separate radio experiment used signals sent between Earth and the spacecraft. As those radio waves passed through Pluto's atmosphere, the gas bent them slightly. That bending allowed scientists to estimate pressure and temperature much closer to the surface. Together, the measurements produced a detailed vertical profile of an atmosphere that had previously been studied mainly through distant stellar occultations. One of the biggest surprises was how cold the upper atmosphere turned out to be. Before New Horizons, several models had predicted temperatures around 100 Kelvin, or somewhat higher in parts of the upper atmosphere. The spacecraft found temperatures closer to roughly 70 Kelvin in important regions, equivalent to about -200 degrees Celsius. That difference mattered because atmospheric temperature controls many other processes. A warmer atmosphere expands more strongly and allows gas molecules to reach greater altitudes. That can increase the rate at which light molecules escape Pluto's weak gravity. Before the flyby, some estimates suggested Pluto might be losing atmospheric gas at rates similar to a comet, with enormous numbers of nitrogen molecules escaping every second. New Horizons found a much lower escape rate. The colder atmosphere was more compact, so fewer molecules reached the altitudes where escape becomes easier. Scientists therefore had to revise their understanding of how Pluto was gaining and losing energy. The main gases were already known. Nitrogen dominates the atmosphere. Methane absorbs sunlight efficiently at some wavelengths and can help heat the upper atmosphere. Carbon monoxide can radiate energy away and contribute to cooling. Atmospheric models try to balance those processes. Incoming sunlight deposits energy. Gas molecules absorb some of it. Collisions distribute that energy through the atmosphere, and molecules eventually radiate energy back into space. If the calculated heating and cooling are correct, the model should reproduce the temperatures the spacecraft measures. Pluto was colder than those simpler calculations expected. At the same time, New Horizons photographed something that had been difficult to appreciate from Earth. After closest approach, the spacecraft looked back toward Pluto with the dwarf planet positioned between the camera and the distant sun. In that geometry, sunlight passing through the atmosphere illuminated a remarkably complex haze. The haze extended more than 100 kilometers above the surface, with multiple thin layers visible around Pluto's curved limb. Some images showed dozens of individual bands stacked above one another. It also produced a faint blue color in enhanced color views. That color does not mean Pluto's atmosphere resembles a blue terrestrial sky. The blue appearance comes from the way tiny haze particles scatter shorter wavelengths of visible light. The particles themselves form through atmospheric chemistry. Ultraviolet radiation interacts with methane and nitrogen high in Pluto's atmosphere. Methane molecules can be broken apart, allowing fragments to combine into larger hydrocarbons and nitrogen-bearing compounds. As those products become heavier, they can form microscopic particles. Those particles gradually drift downward. By the time they approach the surface, some have been transformed through continued ultraviolet radiation and chemical reactions into complex organic material, often grouped under the name tholins. Tholins are not one specific compound. The word refers to mixtures of complex carbon-rich substances produced when simple gases such as methane and nitrogen are chemically altered by energetic radiation. Similar materials help create reddish and brownish colors on several cold bodies in the outer solar system. At first, Pluto's haze seemed like an additional piece of atmospheric chemistry sitting inside a larger climate system. Its layered structure was visually spectacular, but the main thermal models still focused heavily on the gases. The unexpectedly low temperature forced scientists to look at those particles differently. A haze particle can absorb incoming solar energy. It can also radiate infrared energy back into space. If enough particles are present, their combined effect can alter how quickly the entire atmosphere gains and loses heat. That possibility became especially important because Pluto's atmosphere is so thin. In a dense atmosphere, gas molecules dominate many thermal processes simply because there are so many of them. Pluto contains far less gas, making suspended particles potentially much more influential. By 2017, researchers had developed a much stronger version of that idea. They proposed that Pluto's haze could be one of the main reasons the upper atmosphere was so unexpectedly cold, with the particles themselves carrying away far more heat than earlier models had allowed for. The theory made a specific prediction about Pluto's infrared glow. Testing it properly would require a telescope capable of separating Pluto's faint thermal emission from Charon and measuring wavelengths that previous observations could not resolve well enough. In 2017, researchers proposed an explanation that changed the role of Pluto's haze from a visual feature into a major part of the climate system. The idea began with the chemistry occurring high above the surface. Pluto's atmosphere contains methane mixed into a much larger amount of nitrogen. Far above the ground, ultraviolet radiation can break methane molecules apart. The fragments then react with one another and with nitrogen-bearing molecules, gradually producing larger hydrocarbons and more complex compounds. This process is called photochemistry. It simply means that light provides the energy needed to drive chemical reactions. Some of the products remain as gas for a time. Others eventually grow into microscopic particles suspended in the atmosphere. As those particles become larger, they drift downward and help create the layered haze New Horizons photographed around Pluto. Researchers had already modeled much of that chemistry before the flyby. The temperature measurements from New Horizons gave the haze a second possible role. Every atmosphere has an energy budget. Solar radiation brings energy in. Molecules and particles absorb part of that energy, and the atmosphere eventually has to release energy back into space. The balance determines temperature. On Pluto, methane can absorb sunlight and help heat the atmosphere. Carbon monoxide contributes to cooling by emitting infrared radiation. Earlier models had tried to reproduce Pluto's temperatures using processes involving gases such as these. The results remained too warm. The 2017 hypothesis suggested that the haze particles could provide the missing cooling. A microscopic particle can absorb radiation at one set of wavelengths and emit energy at another. Pluto's haze particles receive some energy from sunlight, but they should also release thermal radiation strongly at infrared wavelengths. Infrared radiation is the form of electromagnetic radiation commonly associated with heat. The key prediction involved the mid-infrared, a range of wavelengths longer than visible light and particularly useful for detecting thermal emission from cold objects. If Pluto's haze was radiating efficiently in this part of the spectrum, billions of tiny particles could carry heat away from the atmosphere much faster than gas-only models predicted. That would help explain why New Horizons measured such low upper atmospheric temperatures. It would also make Pluto unusual. In many planetary atmospheres, gases dominate the overall heating and cooling budget. Aerosols and clouds can still be important, but the 2017 Pluto model gave suspended haze particles an unusually large influence over atmospheric temperature. The theory produced something scientists could eventually test. A haze capable of cooling the atmosphere so effectively should also create a measurable thermal signature. Pluto should emit more radiation at certain mid-infrared wavelengths than models without strong haze cooling would predict. There was a practical difficulty. Pluto is extremely cold and extremely distant. Its thermal glow reaching Earth is faint. Charon sits nearby in the sky and produces its own infrared radiation. The two worlds orbit about 19,600 kilometers apart. But from Earth, they are separated by only a tiny angle. Earlier infrared observatories often measured much of the Pluto-Charon system together. That created uncertainty. If a telescope detected more thermal radiation than expected, researchers had to determine how much came from Pluto's surface, how much came from Charon, and how much might originate in Pluto's atmosphere. Separating those contributions required both sensitivity and angular resolution. The haze hypothesis therefore remained compelling without receiving the clean observational test researchers wanted. Several years passed while Pluto continued moving slowly outward through its 248-year orbit. Then, a new infrared observatory began operating about 1.5 million kilometers from Earth. The James Webb Space Telescope carried an instrument designed specifically to study faint thermal radiation at mid-infrared wavelengths. For the first time, astronomers had a telescope capable of measuring Pluto and Charon separately while looking directly into the range where the haze was predicted to release its heat. The instrument that made this possible was called MIRI, the mid-infrared instrument aboard the James Webb Space Telescope. New Horizons had transformed Pluto by showing scientists its surface in extraordinary detail. Most of those famous images recorded sunlight reflected from ice, mountains, haze, and darker terrain. Webb could study something different. Every object with a temperature above absolute zero gives off electromagnetic radiation. Warm objects emit strongly at shorter infrared wavelengths. Extremely cold objects, including Pluto, release much of their thermal energy at longer wavelengths. That thermal glow carries information about temperature and about the materials releasing the energy. For Pluto, the important observations extended through wavelengths from roughly 15 to 25.5 micrometers. A micrometer is 1/1,000,000th of a meter, so these wavelengths are far longer than visible light and completely invisible to human eyes. MIRI was designed to detect radiation in this part of the spectrum. This gave astronomers a way to measure energy, actually leaving Pluto rather than relying mainly on light reflected from the distant sun. There was still a difficult observational problem. Pluto and Charon orbit each other at an average separation of about 19,600 kilometers. That sounds enormous until the system is viewed from several billion kilometers away. From Earth and from Webb's location near Earth, the two bodies appear extremely close together in the sky. Older thermal observations often could not separate them cleanly. Imagine looking at two very small bulbs placed side by side from several kilometers away. If the telescope records them as one unresolved point, the measured brightness represents both bulbs combined. That creates a problem when one of them changes. Pluto has regions with different surface compositions and temperatures. Charon has its own mixture of water ice, darker material, and other compounds. As the two bodies rotate, different terrain faces the telescope. A changing infrared signal could therefore come from Pluto, Charon, or a mixture of both. Scientists call this kind of problem a degeneracy. A degeneracy occurs when several different physical explanations can produce nearly the same measurement. Additional information is needed to separate them. Webb provided that separation. Its combination of sensitivity and angular resolution allowed researchers to measure Pluto and Charon individually in the mid-infrared. They then watched how the thermal brightness of each world changed as it rotated. This produced what astronomers call a thermal light curve. A light curve is simply a record of brightness over time. If a rotating world has warmer and colder regions, its infrared brightness changes as those regions rotate into and out of view. The pattern can reveal differences across the surface. For Pluto, however, the researchers were looking for more than warm and cold terrain. The 2017 haze model had predicted an additional source of infrared radiation above the surface itself. If the haze particles were carrying away a significant amount of atmospheric heat, they should contribute their own measurable signal at mid-infrared wavelengths. That meant the observations had to account for several sources of thermal energy at once. Some radiation came from Pluto's surface. Some came from Charon. A portion might come from Pluto's atmosphere. Separating the two worlds removed one of the largest uncertainties. The researchers could compare Pluto's measured brightness with models of its nitrogen-rich plains, methane-bearing regions, and darker surface materials. They could also model Charon independently, rather than allowing its thermal signal to blend into Pluto's. The remaining excess carried information about the haze. This was a very different kind of look at Pluto from the New Horizons flyby. New Horizons had passed close enough to photograph features only a few kilometers across. Webb remained billions of kilometers away. Its advantage came from wavelength rather than proximity. The telescope was measuring the slow release of heat from a world whose surface sits only a few dozen degrees above absolute zero. When the Pluto and Charon signals were finally separated, the result matched the prediction that had been waiting since 2017. Pluto's haze was emitting detectable thermal radiation, and the amount of energy involved was large enough to show that those tiny suspended particles were playing a major role in controlling the temperature of the atmosphere. The Webb measurements turned the haze hypothesis into something much more concrete. Pluto's atmosphere had looked visually delicate in the New Horizons images, with thin blue layers stacked above the surface. Webb showed that those particles were also carrying a significant amount of heat away from the atmosphere. The key result appeared in a 2025 study published in Nature Astronomy. Researchers used Webb's mid-infrared measurements to isolate Pluto's thermal emission and compare it with models of the surface and atmosphere. The observed signal could not be explained by the solid surface alone. A substantial part of the infrared glow was coming from the haze. That matters because thermal emission is one of the main ways a cold world loses energy to space. The particles in Pluto's haze are thought to contain complex organic material, similar in some ways to the aerosols found in Titan's atmosphere. Models also indicate that hydrocarbon and nitrile ices can coat or mix with those particles as they descend. A nitrile is a carbon, a nitrogen-containing compound. In Pluto's atmosphere, these compounds can form through ultraviolet-driven chemistry involving methane and nitrogen. The resulting particles are extremely small. Individually, they carry almost no energy. Spread through a large volume of atmosphere, however, billions upon billions of particles can become a major thermal component. The Webb observations showed that this effect is strong enough for the haze to play a central role in Pluto's atmospheric energy balance. That phrase, energy balance, describes the competition between energy entering the atmosphere and energy leaving it. Sunlight provides part of the incoming energy. Methane absorbs some of that radiation and helps warm the gas. The haze then absorbs and emits radiation as well, including strongly in the infrared where heat can escape to space. If the haze radiates efficiently enough, the atmosphere cools more rapidly. That cooling changes more than temperature. Temperature affects density. Density affects how the atmosphere expands with altitude. Those changes influence winds, vertical circulation, and the way methane and nitrogen move through different atmospheric layers. The haze, therefore, becomes part of Pluto's climate machinery rather than a passive byproduct floating inside it. Its influence also connects back to the seasonal cycle. As Pluto moves through its long orbit, sunlight changes. That affects methane chemistry and the production of new haze particles. The amount, size, and composition of those particles can then change how efficiently the atmosphere releases heat. Surface nitrogen responds to atmospheric temperature through sublimation and condensation. The result is a coupled system in which chemistry, radiation, and surface ice all affect one another. This is why the Webb result was more significant than simply detecting organic particles. New Horizons had already shown that haze existed. Webb measured what that haze was doing thermally. The result helped explain why Pluto's upper atmosphere had been much colder than earlier gas-only models predicted. It also reduced the need to invoke unusually strong cooling from carbon monoxide alone. The atmosphere could lose a large amount of energy through suspended particles. The idea is unusual enough that Pluto now serves as an important example of an aerosol-dominated atmosphere. Aerosols are tiny, solid or liquid particles suspended in gas. Earth has aerosols from dust, smoke, sea salt, and volcanic material, and they can influence climate here as well. On Pluto, the balance appears much more extreme because the atmosphere is so thin. A relatively small mass of haze can exert an outsized effect on the thermal structure. Nothing in the measurement suggests a poisonous cloud or a biological danger. The scientific result is more interesting than that kind of interpretation. A faint atmosphere surrounding a dwarf planet, smaller than Earth's moon, is being regulated to a surprising degree by microscopic particles created through ultraviolet chemistry. Those particles help determine how quickly the atmosphere cools, how its temperature changes with altitude, and how it responds to Pluto's slow seasonal cycle. By the time Webb revealed that mechanism, another part of Pluto's climate story was beginning to change. Ground-based occultation measurements were showing early signs that the long atmospheric plateau may have ended, with pressure possibly beginning to fall after decades of growth and stability. By the early 2020s, Pluto's atmosphere had been under observation for more than 30 years, long enough for astronomers to begin seeing changes that unfold far more slowly than weather on Earth. The measurements still relied heavily on stellar occultations. During an occultation, Pluto passes in front of a distant star as seen from Earth. The star's light does not disappear all at once. Before Pluto's solid surface blocks it completely, some of that light travels through the thin atmosphere around the dwarf planet. Gas bends the starlight slightly and reduces its brightness. By recording that fading many times per second, astronomers can reconstruct a light curve showing how the atmosphere behaved at different altitudes. Changes in the curve can reveal shifts in pressure, temperature, and atmospheric structure. A recent analysis combined 10 Pluto occultations observed between August of 2017 and July of 2023. That span is short compared with Pluto's 248-year orbit, but it covers an especially important part of its seasonal cycle. Earlier observations had shown atmospheric pressure rising for decades after Pluto passed perihelion in 1989. Around the time of the New Horizons encounter in 2015, that long increase appeared to level off. Measurements through roughly 2021 suggest that the atmosphere remained on a broad pressure plateau. Pluto had continued moving farther from the Sun throughout that period, yet enough nitrogen was still sublimating from the surface to maintain a relatively stable atmosphere. The newer occultations may show the beginning of a change. When researchers compared observations from 2022 with the earlier plateau, they found evidence that atmospheric pressure had decreased. At a reference altitude represented by a radius of 1,275 kilometers from Pluto's center, the estimated decline was about 7%, with an uncertainty of roughly 6 percentage points. That uncertainty is large. A second analysis looked deeper in the atmosphere, at a radius of about 1,215 kilometers, while including the effects of haze. There, the estimated decrease was closer to 16%, with an uncertainty of about 2 percentage points. Those two values are measuring the atmosphere under different assumptions and at different levels, so they should not be treated as two simple readings of the same pressure drop. Together, they suggest that the long period of atmospheric growth and stability may be ending. The physical explanation fits Pluto's seasonal cycle. As the dwarf planet moves farther from the Sun, its surface receives less energy. Over time, major nitrogen reservoirs such as Sputnik Planitia should cool enough for sublimation to weaken. Once less nitrogen enters the atmosphere than returns to the surface, pressure begins to fall. Some atmospheric nitrogen can then condense directly back onto Pluto as frost. That process can continue for decades. The timing is important because Pluto's seasons respond slowly. Its atmosphere did not begin shrinking immediately after perihelion in 1989. Surface reservoirs stored heat and continued feeding nitrogen gas into the atmosphere long afterward. If the recent measurements are confirmed, the delay may have lasted more than 30 years. Astronomers are careful about that conclusion. The 2026 analysis does not claim that Pluto's atmosphere is definitely collapsing, and it does not suggest that the atmosphere is about to disappear. The researchers explicitly state that additional occultations are needed to confirm whether the recent pressure decrease represents a genuine long-term trend. That caution matters, because stellar occultations depend on geometry, atmospheric modeling, haze, and the quality of each observation. A few measurements can hint at a change before enough data exists to establish its full size or duration. Even so, the timing makes these observations unusually valuable. Humanity may be watching Pluto move from one climatic phase into another. The atmosphere first detected in 1988 grew stronger through decades of observation, remained near a plateau around the New Horizons era, and may now be beginning a slow decline as Pluto continues outward. The same occultation data also contained changes closer to the surface. While much of the upper atmosphere remained broadly similar, the lower layers showed signs that Pluto's haze particles themselves may be shifting and settling through the sky. The occultation records contained more than a measurement of total atmospheric pressure. Researchers also examined the exact shape of each light curve as the star faded behind Pluto. Small changes in that curve reveal how different layers of the atmosphere bend and absorb the incoming starlight. The upper atmosphere remained comparatively consistent across many of the observations between 2017 and 2023. Closer to the surface, the pattern changed. The lower part of the light curve developed a different slope, meaning the starlight was fading through the deeper atmosphere in a slightly different way than before. That change could not be explained simply by adjusting the total pressure. One interpretation involves Pluto's haze. The haze particles photographed by New Horizons are created high in the atmosphere through ultraviolet-driven chemistry. Methane is broken apart. Fragments react into more complex molecules, and those products eventually grow into microscopic solid particles. Once the particles become large enough, gravity begins pulling them downward. This process is called sedimentation. On Earth, sedimentation can describe dust or ash slowly settling out of the air. Pluto's version happens in an atmosphere millions of times less dense than ours and over much longer timescales. The 2026 occultation analysis found that the lower atmospheric changes were consistent with haze particles settling on yearly or even shorter timescales. That means Pluto's haze can reorganize significantly within only a small fraction of one Pluto season. A particle formed high above the surface may spend months or years drifting downward through the atmosphere before eventually reaching the ground. Its descent changes the amount of material suspended at different altitudes. That matters because haze affects temperature. Webb showed that the particles are effective infrared emitters, so changing their vertical distribution can alter how different atmospheric layers cool. The haze, therefore, participates in both chemistry and climate while physically moving through the sky. The occultation light curves contained another subtle feature. Some observations showed isolated spikes and small, irregular structures rather than perfectly smooth fading. Researchers interpreted several of these as possible buoyancy waves. A buoyancy wave forms when a parcel of air is pushed upward or downward, and then oscillates around its original level because gravity and density differences pull it back toward equilibrium. Earth's atmosphere contains these waves constantly. Air passing over a mountain range can be pushed upward, then rise and sink in a repeating pattern downstream. Similar waves can form when atmospheric layers with different temperatures and densities interact. Pluto has no dense weather system like Earth's, but the same physics can operate in its thin nitrogen atmosphere. A passing wave can briefly compress one layer while expanding another. That changes how starlight travels through the gas during an occultation, producing small features in the recorded brightness. The effect is delicate enough that it can only be detected under favorable observing conditions. The broader picture is of an atmosphere with internal structure. Its total mass is tiny. Near the surface, pressures are measured in microbars. Above that, the gas becomes thinner still, extending hundreds of kilometers before gradually blending into space. Within that narrow envelope, haze particles settle downward, while atmospheric waves can move material vertically over shorter periods. Those motions happen at scales much smaller than the century-long seasonal changes discussed earlier. A long orbital cycle controls the background climate. Inside that climate, individual atmospheric layers can shift over months and years. Some of the haze eventually reaches the surface and becomes part of Pluto's dark, organic coating. Other molecules follow a different path. Pluto's gravity is weak enough that a fraction of its upper atmosphere can escape entirely. Some of that material travels far enough to interact with Charon, the large moon orbiting only about 19,600 kilometers away. Charon sits unusually close to Pluto in both distance and importance. Its diameter is about 1,212 kilometers, making it roughly half the size of Pluto. That is an unusually large moon compared with the world it orbits. Because of that size, Pluto does not remain fixed while Charon circles around it. Both bodies orbit a shared center of mass called a barycenter. In the Pluto-Charon system, that point lies outside Pluto's surface. The two worlds, therefore, move around an invisible point in space between them. They are also tidally locked to each other. Pluto always shows the same hemisphere toward Charon, and Charon always shows the same hemisphere toward Pluto. One complete orbit takes about 6.4 Earth days. This close relationship allows material to move between them. Pluto's gravity is weak. Its surface gravity is only about 6% of Earth's, and the upper atmosphere becomes increasingly thin with altitude. Some methane molecules can eventually reach high enough above the surface to escape Pluto altogether. Once free, a portion of that material travels through the Pluto-Charon system. Charon is only about 19,600 kilometers from Pluto on average. At that distance, some escaping methane can cross the gap and reach Charon. The effect is especially important near Charon's poles. Temperatures there can become low enough for methane molecules arriving from Pluto to freeze onto the surface. The material does not remain as simple methane forever. Ultraviolet radiation from the distant sun can break the methane apart. Charged particles and other forms of energetic radiation continue processing the material. Over time, fragments recombine into larger carbon-rich compounds. This kind of radiation chemistry produces reddish organic material similar to the tholins found on Pluto. New Horizons saw a dark reddish region near Charon's North Pole. Scientists named it Mordor Macula. Models developed after the flyby showed that methane, escaping from Pluto, could help explain how some of that coloration forms. The process is slow. Individual methane molecules arrive in tiny amounts. During Charon's long polar winter, some can remain trapped on extremely cold ground for years. When sunlight eventually returns, much of the simpler methane can escape again. A fraction, has already been chemically transformed. That processed material is less volatile and stays behind. Over many seasonal cycles, the residue can accumulate into a darker polar deposit. This creates a direct chemical link between the two worlds. Gas leaves Pluto. Some of it crosses thousands of kilometers of space. Radiation then converts a small fraction of that transferred material into compounds that can remain on Charon's surface for much longer. Webb later revealed additional chemistry on Charon that needs to be treated separately from this methane transfer process. In 2024, observations with the James Webb Space Telescope detected carbon dioxide and hydrogen peroxide on Charon's surface. Hydrogen peroxide can form when energetic radiation repeatedly alters water ice. A high-energy particle can break bonds inside water molecules. The fragments can recombine into new molecules, including hydrogen peroxide. That makes the detection useful as a sign of radiation processing on Charon's icy surface. The carbon dioxide appears to have a different history. Researchers have proposed that much of it may come from material already present within Charon, potentially exposed from below by impacts, with additional surface chemistry modifying it over time. That distinction matters. Charon's reddish polar material can be partly connected to methane escaping from Pluto, while the newly detected carbon dioxide and hydrogen peroxide involve their own sources and chemical pathways. Taken together, these processes show how active the Pluto-Charon environment can be, despite containing almost no dense gas between the two bodies. Pluto's atmosphere feeds a small stream of material outward. Charon's cold surface can trap some of it. Radiation continues changing whatever remains exposed. The two worlds have been exchanging energy and material through this system for billions of years. Yet the most surprising recent evidence from Pluto involves movement in the opposite direction. Instead of gas escaping upward from the surface, new analysis suggests that liquid nitrogen may sometimes rise from beneath Sputnik Planitia and reach the top of Pluto's largest glacier. Along the northern edge of Sputnik Planitia, some of the darkest features in the glacier had been sitting inside New Horizons images since 2015. They appeared around the enormous polygonal convection cells that cover the nitrogen ice. Some were narrow, dark lines tracing cell boundaries. Others were broader and more diffuse, spreading outward from those boundaries into nearby terrain. For years, those markings were interpreted mainly as part of the complicated surface structure of the glacier. Then, researchers looked at them again. The newer analysis brought together planetary scientists who study Pluto and glaciologists familiar with how ice behaves on Earth. They noticed that some of the darkened patterns resembled terrestrial glaciers after liquid water has spread across the surface. On Earth, a glacier can darken when rain wets the ice, or when meltwater emerges from below and spreads into low areas. The Pluto features showed a similar relationship with the local topography. The dark material often followed narrow boundaries between convection cells and extended into nearby depressions. That resemblance led researchers toward an unusual explanation. Liquid nitrogen may have reached the surface. NASA announced the result on August 5, 2026, following publication of the study on July 31st. The evidence came entirely from New Horizons images collected 11 years earlier. Sputnik Planitia covers roughly 1 million square kilometers and is larger than Texas and Oklahoma combined. In the northern part of that glacier, the convection cells are enormous, with individual structures comparable in width to cities. Researchers proposed that nitrogen may occasionally melt near the bottom of this thick ice sheet. This is called basal melting. The base of a glacier exists under very different conditions from its exposed surface. Kilometers of ice press downward, increasing the pressure. Heat escaping slowly from Pluto's interior also reaches the glacier from below. At the surface, nitrogen remains solid or passes directly into gas. Several kilometers down, temperature and pressure can move the nitrogen closer to its melting conditions. If a small amount becomes liquid there, it behaves in a particularly useful way. Under the relevant conditions, liquid nitrogen can be less dense than the surrounding solid nitrogen ice. That gives it buoyancy. Liquid forming near the base can therefore move upward through cracks rather than remaining trapped underneath the glacier. The trip is difficult because the upper ice is colder. Any liquid rising through it begins losing heat and could freeze before reaching the surface. The new study argues that some pathways may allow the nitrogen to rise quickly enough to survive that journey. Once it emerges, the liquid could spread across nearby low ground before freezing or evaporating. That process would temporarily wet the glacier. It also provides a possible explanation for the dark, linear, and diffuse features photographed by New Horizons. Rain cannot explain them. Pluto's atmosphere is far too thin, and its surface conditions do not allow liquid nitrogen to condense into falling raindrops and remain liquid on the way down. Any liquid on the surface would therefore need another source. The proposed source lies underneath the glacier itself. This interpretation remains evidence-based, rather than a direct observation of flowing liquid. New Horizons did not photograph a river of nitrogen moving across Pluto in real time. Scientists are working backward from the shapes and locations preserved in the terrain. The researchers found that surface wetting by nitrogen emerging from below can reproduce important features of the observed pattern. If the interpretation is correct, it represents the first evidence for recently flowing liquid on Pluto. That wording is important. The liquid would probably be temporary. Pluto's exposed surface is too cold, and its atmospheric pressure too low for stable pools to remain for long. A small flow could emerge, spread through a depression, then freeze or vaporize. The marks it leaves behind can survive much longer than the liquid itself. The discovery also changes the meaning of Sputnik Planitia once again. Earlier in the journey, the glacier appeared active because solid nitrogen was flowing horizontally. Its polygonal cells then revealed solid-state convection from below. Now the same region may contain a third kind of motion, with nitrogen briefly becoming liquid at depth and forcing its way upward through the ice. A glacier that looked smooth and quiet from billions of kilometers away may contain solid circulation, seasonal sublimation, and occasional basal melt, operating on different timescales. All of those processes require energy. Some comes from sunlight striking the surface. Some may come from heat stored inside the glacier. The possibility of basal melting pushes the story deeper into Pluto again, because maintaining conditions warm enough for liquid nitrogen beneath several kilometers of ice depends on how much energy this small world has managed to retain for more than 4 billion years. The activity seen across Pluto comes from several different energy sources operating at different depths and on very different timescales. Near the surface, sunlight drives much of the visible nitrogen cycle. Even at billions of kilometers from the Sun, the small amount of solar energy reaching Pluto is enough to warm exposed nitrogen ice slightly. That warming increases sublimation, allowing solid nitrogen to enter the atmosphere as gas. Later, when temperatures fall, some of that gas condenses back onto the ground. This exchange helps move nitrogen from one region to another and controls much of Pluto's atmospheric pressure over its 248-year orbit. Sputnik Planitia adds another layer of activity. Its nitrogen glacier may be several kilometers thick and a deposit that deep can transport heat through convection. Heat entering the lower part of the glacier makes some nitrogen ice slightly warmer and less dense. That material rises slowly. Cooler material near the surface sinks along the edges of the large polygonal cells. The process can continue while the nitrogen remains solid. Convection is more efficient at moving heat than simple conduction. Conduction transfers energy molecule by molecule through stationary material, much like heat spreading through the handle of a metal pan. Convection physically moves warmer material from one place to another. Inside Sputnik Planitia, the soft mechanical behavior of nitrogen ice allows that second process to operate on a scale of kilometers. The possibility of basal melting adds phase changes to the energy balance. When solid nitrogen melts, energy is absorbed without immediately producing a large increase in temperature. When liquid nitrogen freezes again, that stored energy is released. This energy associated with changing phase is called latent heat. The same principle is familiar on Earth. Melting ice can absorb a substantial amount of heat while remaining near its melting temperature. On Pluto, nitrogen can perform a similar role under completely different pressure and temperature conditions. Deeper inside the dwarf planet, sunlight becomes irrelevant. Pluto contains a rocky interior rich in elements that were incorporated when the solar system formed more than 4.5 billion years ago. Some of those elements are radioactive. Long-lived isotopes of uranium, thorium, and potassium decay slowly over billions of years. Each decay releases a small amount of energy. Across an entire rocky interior, those tiny releases add up to a continuing source of heat. This radiogenic heating is one reason small, icy worlds do not necessarily become completely cold inside. The important issue is how quickly that heat escapes. Pluto's outer shell is dominated by water ice, which conducts heat relatively poorly compared with many rocky materials. A thick ice shell can therefore act as insulation. Heat produced in the rocky interior must travel through tens or perhaps hundreds of kilometers of cold material before reaching the surface. If an internal ocean exists, it changes that thermal structure further. Liquid water can transport heat differently from solid ice. As portions of an ocean gradually freeze, latent heat is released, slowing the cooling process. Compounds dissolved in the water can also change when freezing occurs. Ammonia is particularly important because it lowers the freezing temperature of water. A mixture containing ammonia can remain liquid at temperatures well below the freezing point of pure water. That makes it easier for small pockets, slushy layers, or perhaps a deeper ocean to survive inside a world whose surface is extraordinarily cold. None of these mechanisms alone needs to power everything observed on Pluto. Seasonal frost transport can be driven mainly by sunlight. Nitrogen convection depends on conditions inside the glacier. Possible cryovolcanic activity and a subsurface ocean require heat stored much deeper within the dwarf planet. The different processes overlap, but they do not all share the same energy source. That distinction helps explain why Pluto can look active without requiring an extraordinary hidden furnace beneath the surface. Its behavior emerges from familiar physics, operating under unusual conditions. A small amount of sunlight can move volatile ice because nitrogen sits close to its sublimation temperature. A modest internal heat flow can matter because thick ice traps energy efficiently. Long-lived radioactive elements can continue releasing heat billions of years after Pluto formed. The result is a world whose surface, atmosphere, glacier, and interior evolve at different speeds. Some changes happen over years. Others take millions. And because humanity has observed Pluto closely for only a tiny fraction of its orbit, new horizons may have arrived during a remarkably temporary stage in that much longer evolution. Pluto reached perihelion in 1989. the point in its orbit when it was closest to the Sun. That moment came only 26 years before New Horizons arrived. For a world that takes about 248 Earth years to complete one orbit, 26 years is a narrow slice of time. New Horizons reached Pluto while the dwarf planet was still relatively close to the warmer part of its long seasonal cycle. That timing may have mattered enormously. Pluto had already begun moving farther outward by 2015, but its atmosphere remained surprisingly substantial. Nitrogen was still sublimating from the surface. Haze layers extended high above the ground. Volatile ices continued moving between different regions. New Horizons therefore encountered a Pluto that was still actively exchanging material between its surface and atmosphere. If the spacecraft had arrived many decades later, some of those conditions might have been different. The flyby itself lasted only hours, but the data returned much more slowly. At Pluto's distance, radio signals required roughly 4.5 hours to travel one way between the spacecraft and Earth. New Horizons also transmitted data at only around 1 to 2 kilobits per second during much of the downlink. That is extraordinarily slow by modern standards. A basic photograph on a phone can contain several megabytes. New Horizons had to return an entire scientific encounter dataset across billions of kilometers through a communications link, moving only a few thousand bits each second. The complete Pluto encounter dataset contained about 6.25 gigabytes. Transmission continued for more than 15 months after the flyby. The final portion arrived in October of 2016. Scientists then had years of work ahead of them. Each image could be reprocessed. Different datasets could be combined. Surface features that seemed ordinary in one analysis could become important when compared with laboratory experiments or observations of glaciers on Earth. That is exactly what happened with the dark features in Sputnik Planitia. The images had been sitting in the New Horizons archive since 2015. 11 years later, researchers recognized evidence that liquid nitrogen may have risen through cracks in the glacier and reached the surface. The spacecraft had already left Pluto far behind. The discovery was still waiting inside the data. Webb added a different kind of observation. Instead of flying close to Pluto, it can return to the system from billions of kilometers away and measure thermal radiation over time. Its mid-infrared observations showed that Pluto's haze contributes strongly to the atmosphere's heat balance. Ground-based stellar occultations provide another piece of the timeline. They allow astronomers to keep measuring atmospheric structure year after year as Pluto moves farther from perihelion. The newest analyses suggest that the long-pressure plateau may have begun to weaken sometime in the early 2020s. That trend still needs confirmation. If it continues, astronomers may be watching the atmosphere enter a new seasonal phase that no spacecraft has ever observed up close. Future occultations could show pressure continuing to fall. Webb could measure how haze emission changes as temperatures shift. Surface nitrogen may gradually migrate into new regions as Pluto receives less solar energy. The world, photographed by New Horizons in 2015, may therefore represent only one temporary version of Pluto. Its atmosphere was relatively robust. Its great nitrogen glacier was actively convecting. Its volatile surface was still responding to heat stored from earlier parts of the orbit. Those conditions will not remain exactly the same forever. This makes the timing of the flyby feel unusually fortunate. Humanity reached Pluto once, during a brief encounter in the middle of a climatic cycle lasting centuries. The spacecraft stayed only long enough to collect a snapshot. More than a decade later, that snapshot is still producing new discoveries. The history of Pluto has followed the same pattern from the beginning. A faint moving dot became a world with a moon. A nearly featureless disk became a landscape of glaciers and mountains. A cold atmosphere became a climate controlled partly by microscopic haze particles. The deeper scientists look, the older, simple picture becomes harder to maintain. The frightening part of Pluto was never a hidden creature or some single impossible object waiting on the surface. It was the realization that the quiet, frozen world scientists expected had never really existed in that form. Pluto is still changing. Our understanding of it is changing with it. And beyond Pluto, thousands of colder Kuiper Belt objects remain so distant that many are still little more than points of light. If the first one we examined closely contained this much hidden activity, the outer solar system may still be full of worlds whose most important processes are waiting for us to become capable of seeing them.